tall guy. Thank you. Okay, I think we'll get started. So, good morning. I'm Rick Lancaster. I'm the Biosolids Director at Atkins. This morning we'll be talking about biorefineries in a circular economy. Thank you very much for those people who've managed to make it this morning from the either not getting a flight or from the gala dinner last night. So I think there's a few people with sore heads this morning. I think the keynote was missed as well. So it was a good night. It was a very enjoyable evening. We had lots of food and lots of drink. I think I left the bar at 1 o'clock and there was lots of people drinking lots of alcohol. So I'm not surprised we got a small audience this morning. I'd like to thank the sponsors, a number of which will be sat on the panel today. And what I'd like to do first is introduce the panel. So we have Frank Rogalla, who's the Director of Innovation and Technology at Aqualia. Dr. Malcolm Fabyi, who's the Chief Operating Officer at Drylet. Harald Kleiven from CAMBI. I'm sure you all know Harald. Harold's always at these events. And Miguel-Sanz, who's the Director of Strategic Development at SUEZ. John Brigg from Yorkshire Water, unfortunately, was not allowed to travel. Yorkshire Water, due to the coronavirus, have banned travel to Europe. But there you go. Okay. So I will start with a few slides to kind of stimulate some thinking around this subject. And obviously, with my title, there's going to be a bigger focus on biosolids. Okay, just before I do that, so just so you understand who we are, Atkins is a global consultancy and operator of infrastructure. We're part of the S&C Levelling Group. We have 55,000 employees spread across the world, and we work in about 50 countries across the globe. Okay, so why is biosolids the lifeblood of a circular economy? You ask. Well, it's black gold. So there's lots of really good stuff in this. So the obvious stuff, phosphorus. There's water. So if you've got agriculture and you haven't got a lot of water, then this is a good source of that. Source of carbon. It's got methane. There's energy. Depending on how you treat it, you can have somewhere between 400 and 800 kilowatt hours per tonne dry solids. It's really good stuff. And there's cellulose and all kinds of really good stuff in it. And we can mine all of these things. There are also a few nasties in there, so there's metals. In the UK, we used to have metals in sludge when we had an industry, and our strategy's been to completely destroy our industry so we don't have metals anymore, and we can recycle to agriculture. There's some pathogens in there, and there's also some organics, which is it's an area where there's a lot of interest at the moment. Most operations in the UK, I would say about 50% of their carbon footprint comes from biosolids, even though recycling into agriculture replaces inorganic fertilizers, which produce lots of carbon footprint. It's still a carbon footprint that's associated to the company. And there's some conversations I know that we're going to be having today around how we can reduce sludge and sludge production. So transport and treatment and disposal has got a big carbon footprint. It's also a big cost to the industry, 30 to 50% I've heard quoted in terms of overall OPEX costs. So it's big numbers. And we produce a hell of a lot of it, and we're producing a hell of a lot more. The number is going up and up and up. So depending on what literature you read, you'll get different numbers. And depending on how people calculate how much sludge they produce in the first place, you'll get different numbers. But just in the UK, it's about 1.5 million tonnes dry solids per annum, which is about 30 million metres cubed. And this is the bit I like. And that's essentially enough to fill Anfield a lot of times. And I know Francois will really appreciate me saying this. It's roughly 48 or every home game if you're an Everton fan. So I thought what I'd do is I'd pick one of these. So I'm going to pick cellulose, and 80% of the toilet paper is cellulose. And here's some really interesting fun facts for you. About 57 sheets are used a day. You know, about 8.5 per visit. I know what you're all thinking. You're thinking, wow, this guy, I really need to invite him for dinner sometime. What a great conversation we could have with my family. And there's a roll of honour here as well, and we can see that the Americans win 12.7 kilograms. So, USA. We are first, woo! Well, we've only come third place again. Okay, so there's a lot of this stuff in there, and it's got a value, and it can be used in things like asphalt, and it can be used in as an insulator in wall insulation. So, again, the point I'm trying to make here is there is value in there, and it's not always obvious. Okay, so move on to my next slide if it catches up. So, biorefineries, energy factories, whatever you want to call it. This is not a new concept. This has been going on for a long, long time in the food industry. We were talking yesterday, and there was a guy from the Netherlands who was talking about energy factories. This is not new. So essentially, you've got wastewater going in, whether that's domestic or industrial, via the sewer. You've got potentially import of using vehicles, and then you've also got some where they'll have a mixed waste stream. So that could be manure, it could be organic waste, it could be domestic food, or it could be industrial waste. Ultimately, all of that stuff comes in, and then we get some good stuff out. So we could just use the wastewater for agriculture, or returning that to the environment. We can create fertilizer, so that's either directly applying sludge or creating pea fertilizer from the pea that's within the wastewater. We produce energy, we produce biofuels, we produce heat. So there's loads and loads of really good stuff here that's already been done in different places all over the world. And more recently, you've got a lot of stuff around biopolymers, bioplastics. Okay, so and again, the cellulose piece comes in here. And if you've got a combined sewer, so that's one that takes the wash off the roads as well, you'll probably get a lot of grit. And grit can be washed and recycled and used as an aggregate. So there's lots of really good stuff. People pay us to take this off them, which is the amazing bit. They give us money to treat this wastewater, and essentially they're giving us loads and loads and loads of value, as you can see from that picture there. Okay, so circular economy, the Ellen McCarthy Foundation. So this is all about keeping, reusing the waste as much as we possibly can, making products, and also thinking about how we can utilise not just those products, but the assets that we own, and making that a circular economy. So we could look at the electricity, we could look at the recycling the materials, or we could look at the water use, as we said before. And you can do lots of those across each other. But in the UK, we have a saying about having your cake, eating your cake, and still having your cake. So we need to make sure we decide which way we're going to go and how that fits within the environment that we have to maximise the opportunity to exploit these valuable resources. So the first things we need to consider when we're doing this, however, is how does it fit with our people? And I think people's a really important factor here, and it quite often gets missed. How does this embed with our organisation? Are our people capable of delivering these new technologies? Are our people bought into the concept? Do they understand the changes in the ways of working? Are they working to the best they can possibly be already to allow this to be implemented within their organisation? The legal framework, a lot of the legal frameworks are based on a linear economy. They don't lend themselves to it. In the UK, waste, water and food waste, if you put it in the same asset, it's going to cost you more. You need different permits, you need different requirements. The cost. So there's a benefit from economies of scale on a lot of these things that are not always going to be beneficial at all of the different treatment plants across the planet. The cellulose one, for example, to put that in, you would need a reasonable sized plant to justify doing it. If you haven't got a number of facilities, does it still work? The markets. Is there a sustainable market for the product that you're producing? Does it have a value? Does it justify the expenditure up front that you're going to put in to ensure that you get some return on your investment? Emerging issues. So we mentioned PFOS earlier on. So these are fire retardants, and they're also used for stain protection. So this is a persistent organic pollutant, and there's a lot of conversations about this. Atkins have done a huge amount of work with the UK water industry and the regulator to look into PFOS and other persistent organic pollutants over the last 10 years. This is the emerging issue that people, the latest fear about biosolids is all the organics in it, and this is being applied to agriculture. And ultimately, this comes down to our stakeholders. And the issue that we tend to miss is that ultimately you are reliant on somebody being comfortable with you applying sludge to agriculture. The UK is now 100% recycling to agriculture. The regulations allow you to do that. Perceptions from stakeholders could stop you doing that tomorrow if there was a big enough scare. So having a sustainable outlet is really, really important. And integrating it within your asset base as well. So quite a lot of the water industry, the asset base is quite old. It's not all brand new and shiny, and integrating some of this technology into that aging asset base is sometimes quite difficult to do. So I'm going to shut up and allow these guys to talk to you about some specific examples of circular economy. Okay, thank you very much.
Thanks, Richard. I'm Frank Rogalla with Aqualia, and my biggest ambition is to get Richard out of a job, so there is no more director of Biosolids, because we make Biosolids disappear. Obviously, we have a lot of time until that happens. Maybe you will be retired by then, but it will happen. So let me tell you a little bit what we have been doing in Aqualia over the last 12 years. When I started my job in 2008, people told me, you have zero money, zero people, go and do research. And now, 12 years later, we have like 35 people and a budget around 5 million per year that we beg from the European Union, most of it. Aqualia manages water services in about 1,000 different communities in about 20 countries. And with that, of course, comes a lot of little toys, about 500 wastewater treatment plants, 250 drinking water plants, to provide services for about 20 to 25 million people. And of course, in Spain, we have this wonderful Roman architecture that brings us water, and we still do the same thing as we did 2,000 years ago with linear infrastructure.
Thank you, Frank. Just to take my city, I was born in Segovia.
Fantastic. Well, this is obviously a thing you should visit if you come close to Madrid. It's only a half an hour train ride to see this marvel of Roman architecture. But, of course, all this infrastructure produces sludge. Why? Because we put in a lot of electricity to produce something that is useless. And I told my chairman, well, every year Aqualia pays an electricity bill of about 30 million euros. Just give me 10% of it, and I will get rid of your energy bill in 10 years. So that is because in the wastewater itself, of course, there is energy, much more energy than we need or that we use today as electricity to destroy the values that are in there. So that was our thinking. How can we harvest this energy? How can we harvest the resources? How can we avoid the expense that we put in today that doesn't make much sense, but it's heritage that we have to live with? And that was our first idea, that actually we can move our cars with our wastewater. And today I'm very proud that every week I drive up to a wastewater treatment plant in Madrid and fill up my car with green biogas. But of course it's a long way. We have, as Richard said, a lot of infrastructure that has been built over many decades with billions of investment that we cannot just dynamite and renew. So we have to go step by step, and one step is of course to tweak whatever is there to make it more efficient. That's why we worked a lot of anamox, because those are bacteria that consume much less energy, that produce much less sludge, and slowly we bring it from the waste line to the mainstream wastewater, and probably in 5 or 10 years most of the wastewater treatment plant will use anamox bacteria in the mainstream to reduce both energy consumption and biosolids production. But of course that's not enough just to tweak the existing steam engine. We have to actually come up with a new paradigm. And that's where, of course, all of you with your clever thinking can come up with new ways to redesign, to rethink, to reorganize certain things. And as Richard said, there's a lot of stakeholders that will resist, that need to be convinced, that will bring inputs as well. And I think that's where our work is still very challenging, to bring all these ideas together and make it happen, because each situation, of course, is local, and you have to adapt to climate and history and culture and your stakeholders before you revolutionize the whole system. But as we have, as I said, 500 little playgrounds, each one we can test a little thing, and we have now about 10 European projects, both live, Horizon 2020, FP7, where we go to various places, whether it's Denia here in the Valencia province, or Lerida in Catalonia, or Almeria in Andalusia. We are all over the territory and try to be circular in our thinking. And here you can see all these projects that actually are also along the whole cycle of water, whether it's desalination with recycled membranes, or whether it's avoiding sludge by using sludge as an absorbent for odors, for instance. So a lot of things can be redone and rethought, but of course cost is still a major factor. Is it cost effective? Under what conditions? Because if you think about fertilizers, for instance, the fertilizer companies are used to having thousands of tons in one location. Now we will tell them we have a few kilograms in 1,000 locations. So it's not exactly the same logistics that you have to organize. One of the projects that allowed us to get rid of energy consumption and biosolids production was memory. This is an anaerobic membrane bioreactor. So instead of pumping electricity into the wastewater, you actually generate biogas directly from the wastewater, and you get rid of all the conventional solids treatment trains, because in that same reactor you degrade the solids and you get disinfected effluent at the end thanks to the membrane. So that has been rather successful as a demo, and it allows you, of course, to rethink wastewater treatment, because you now have a little box that you can place wherever your wastewater system is. Place that little box that will generate energy and generate reused water. But of course, it is a change in paradigm, and you have to convince people that it's actually feasible and cost effective. It's easier, of course, if the wastewater is concentrated and hot. Therefore, in industries, we managed to get a few things going, but also we have now 2 municipal systems where we use anaerobic membrane reactors directly on municipal effluent. In Spain, of course, it's easier than in other territories where the water is colder. So that is a limiting factor, of course, but it's also an advantage, and to analyze your local conditions and not always do what Manchester did in 1914, because what does Manchester in 1914, when activated sludge was invented, have to do with Madrid in 2020? And that's, of course, once you go to the Middle East or to South America, there's a lot of opportunities. And we systematically explore with many partners all the opportunities. We are an open system. Aqualia is just an operator. We're not a technology provider. We work with many different universities, many different suppliers to come up with this original solution for each site, in cover with another big project where we tried at the time to produce bioplastics, biofertilizers, biofuels, all of these by rethinking the way we operate our wastewater treatment. And one of the more spectacular examples we put in was actually the algae biofuel plant that is operating in Chiclana, where over 10 years we reinvented wastewater treatment. Although it's just an old algae pond that had been around for 50 years, we just tried to optimize it systematically so it can produce biofuel and have 0 energy consumption, and a net energy output of 4 times more energy is being generated than you put in. And with that, of course, you can fuel a lot of cars. Since in Spain we are football crazy, we all put it down to, as Richard also said, Anfield. Anfield and Liverpool is a reference. We'll take the pitch of Anfield or take the pitch of Real Madrid. It's 1 hectare of football field. 1 hectare of a football field, if you fill it up with algae, can treat 1,000 cubic meters per day. There's about 5,000 spectators. The wastewater of 5,000 spectators would be used on this pitch to grow algae, and that algae can produce you about 100 tons of biomass per year. At the same time, you have saved the energy for about 20 households, so all the players on the pitch don't have to pay any more electricity bills. And with that 100 tons of biomass, you can actually fuel 20 cars. So also all the players on the field don't have to pay the fuel bill for the Ferraris. So that is the result of this algae project, that with 1,000 cubic meters per day, you can save the energy bills of 20 households and fuel 20 cars. And I think with that, there's many communities that can use this to fuel their vehicles. Of course, that is just the base of the treatment plant, and you can make it smarter and smarter, but my feeling is that it doesn't make sense to put all the digital services on a steam engine. You have to be a more clever paradigm from the start and combine the smart systems, of course, with the new approaches and often decentralized approaches. And I think that is now the enabler. The digital infrastructure enables us to think in a more decentralized way, to capture many different signals, to manage 1,000 different plants rather than concentrate everything in one central location. And we, of course, try that as well to optimize our services and see what can we achieve with conventional infrastructure. And in Santander, we have a case study where for the last 10 years, we've been systematically putting in all the sensors possible. And what you can see over the years is that you can reduce the water consumption by maybe 25%. With that, you can reduce the energy used by maybe 30%, less pumping, less breakage, less movements. But that's not a paradigm shift. 30% savings will not save the carbon footprint of the world. So that's why we always have to go a step beyond and do something more revolutionary. And one concept we are testing right now is the decentralized wastewater treatment plant. Think of it that each building will have a little washing machine for their wastewater, out of which comes clean water, clean energy, clean nutrients. And hopefully with digitalized services, we'll be able to manage these little treatment plants all over the cities. Just like in Japan, they do have recycle plants in every buildings. Probably you can have the same in our urban settings. And of course, as I said, we do that in teams, European teams with many different partners, and that's where the wealth comes from, the diversity of thinking and the diversity of approaches that will allow us to adapt to all the different local situations. And with that, I can show you this little building we have in Vigo, where we actually do have this little decentralized plant in the bottom with an anaerobic MBR that generates both nutrients and energy, but no more sludge. And Richard, soon you'll have a tough time looking for a new job. So thank you very much.
Thank you, Frank. So fantastic, real pushing the boundaries of what we can do with wastewater and how we can save Real Madrid players more money, because they need that. All right. Okay, so can I ask the next speaker to come up? So this is Dr. Malcolm Fabyi, and he's the COO of Drylet.
Thank you. It's a pleasure to be part of this panel. My approach today would be to maybe challenge the way we think about wastewater treatment. When we talk about refineries, so we're borrowing the word refineries from the most common refining we know is petroleum refining. And if we go to a petroleum refinery, there's something we expect to see. It's a very detailed process. The crude coming in, we know exactly what is in that crude to the most minute element that it contains. If we go into the fractionating columns, we know exactly what the height of that column is. We know exactly what happens at each step. Here's the reality. We know more about how far the distance from Earth to the moon than we know about what is inside a wastewater plant. There are many seasoned operators here. If I asked anybody here to tell me what microbes they have. So when we start talking about biorefining, we're going to the next level, right? If I said, what microbes do we have in a wastewater plant? At a high level, we'll talk about heterotrophs, we might talk about nitrifiers, but the specific things that we have in that system that allow us to take wastewater treatment from just the high-level treatment, the heuristics-driven treatment that we do, to actually starting to create products, we're still very, very far from that. So my contention today in the discussion I'm going to have is to try to outline what I believe the gaps are that will need to close if we're serious about turning this into a real economy. So fundamentally in biorefining, I completely agree with you that we're starting with biosolids. Everything we're trying to capture is actually trapped within a bacterial cell. And the first challenge that we have, I think, in most wastewater treatment, as far as the biorefining is concerned, is how do we get more out of that bacterial cell? Our best digesters give us only 50% recovery. So even from the fundamental concept of biorefining, the starting point is already limited. We only get 50% out of it. So how do we get more? We know what the answer is. The answer is we need to lyse those cells more effectively. And technologies like CAMBI, thermal hydrolysis, technologies like biocatalysis can potentially offer us that opportunity. So the first thing is in my view, there's six basic issues here that we need to address. I think the first is, how do we unlock more value from those cells, the fundamental source of all the value that we're deriving? Locked in that cell is the biogas. Locked in that cell are the nutrients that we're trying to recover. The next one is the efficiency of the process itself. And then I think the third one, and Frank alluded to this, is the viability of the solutions that we have. We've been talking about biorefining and how we would unlock the value from sludge for at least 2 decades. For at least 2 decades. The challenge we have is economics. A lot of the solutions we have are just simply non-economical. But there are some interesting ways that we can potentially make them economical. And those are some of the things that I would want to challenge us with. And I also identify some snippets of opportunity that I've seen in terms of how we actually begin to make these processes more economical. The fourth one is, we're generating all this methane. Take the US, for example. Only about 20% of the biogas we generate in the US in wastewater plants is utilized. The bulk of it is flared. Because unlike Europe, we don't have policies that encourage you to actually convert that gas into energy. I remember when I was doing a lot of work on the solid side in Europe, we were seeing things like 10, 15, 20 cents per kilowatt hour incentives in Europe. In the US, energy costs are like 3 to 4 cents per kilowatt hour. That's what you get off of the power grid. Many facilities have zero incentive. So why would they take biogas and convert that to energy? Economically, it doesn't make any sense. But there are now technologies like methanotrophy, where the biogas is actually the feedstock for generating materials. Where instead of burning the gas, because it doesn't make economic sense to burn the gas, I can actually take the gas and it becomes the feedstock for another process. Where the gas is actually a raw material, where I can use that gas to generate polymeric materials for fabrics. And it's not just, or to generate materials for animal feed. And it's not theoretical. There are companies already doing this, companies like Calista, that are already actually commercially viable, companies like Mango Materials, that are actually generating PHAs and PHBs from biomethane and using it to make products. So part of the questions, and it leads to the fifth point, which is the fact that we need innovative business models. So as I indicated earlier, there are policy constraints in some markets. Certainly the market that I'm based in, which is the US market, we have a number of policy constraints. We don't have as much incentives as our European colleagues would have. But we're starting to see some really innovative business models. So for example, in our company, Drylet, we do a lot of work in helping to boost anaerobic digestion. Our biggest market today is actually not wastewater. What is emerging as one of the large markets we're focused on is a lot of developers. These people have nothing to do with wastewater treatment. They are financiers. They are entering into the RNG space because cattle manure and swine manure offers interesting opportunities. And so what we're starting to see is people actually bundling financing together and just buying out not buying out farms, but just buying out the anaerobic digestion portion of what happens in a farm. Because the reality might be that, you know, we are wastewater treatment, we are operators. We may not necessarily be the best people to actually run the biorefining part of our operations. We may not have the capacity to do it. We may not have the ability to do it. Frank talked about the logistics. We may not have the ability to actually tie together all the resources that are close to us. But somebody from the outside might actually be in a better position to do that. And then the final step I'll quickly talk about is the fact that we also need interesting partnerships. Partnerships that are more commercially focused, partnerships that are really focused on unlocking as much value as is possible. I'll now go into just a few points. We've talked about anaerobic digestion. I think, you know, if we go back to the source, as I indicated earlier, only 50% of that starting material that we have is currently being unlocked. Why can't we get more? We know we can get more, but it's, you know, so far it's been well over 20, 30 years, to my knowledge, at least since I've been involved in the field in the last 20 years. We've been chasing this, this basically has been what all of us have been going after. The technologies are there. What I believe the opportunities are is, you know, how do we boost lysis? How do we enhance the generation of biogas? How do we reduce the cost and the energy footprint of increased lysis? And how do we minimize all the operational issues that we might have in co-digestion? The challenges are straightforward. Digestion is a complex process. We're trying to do 3 things in a single reactor. And if we came at this from a process engineering perspective, there might be some interesting things we might be able to do. Lysis is also a very targeted thing. There are 3 different processes taking place in a digester. We're not trying to improve all 3. There are some digesters, and that's part of the challenges that I think we have, is there are some digesters where the fundamental problem we have is the first step, which is hydrolysis. That's true for wastewater. But if I go to a food waste digester, hydrolysis is not their limiting step. Their limiting step is actually operational challenges. Their limiting step in a food waste digester tends to be the 3rd one, which is methanogenesis. There's too much of the first 2 steps taking place and very little of the methanogens in the back end. In the work we do a lot of genomic analysis. And when we do it, it's actually the first time that many of these plants have ever looked at the microbes in their system. We get shocked when we look at the genomics of digesters. So a typical digester, for example, would only have about typically no more than 2 to 3% of the total bacterial population would be methanogens. But that's the engine that transforms all you have into biogas. So if we do too much of the first 2 steps, we can actually overwhelm the methanogens. So it means that if we're going to be serious about biorefining, we have to actually begin to do a lot more in the wastewater plants than we do now in terms of really fundamentally understanding what's going on at a mechanistic level. Cost, obviously, is always an issue. Methanotrophy, I'm actually particularly excited by this. And with methanotrophy, what we're doing is, so it was actually discovered as many of the things we find accidentally. Scientists were baffled that they were not seeing more methane in the atmosphere than is implied by what should be happening. So, you know, in deep hydrothermal vents, we're generating all this methane, yet you don't see it in the atmosphere. And then we started to realize that we actually have a methane sink, that we have these organisms called methanotrophs that take methane as a raw material and convert it into other things. So as I told you, in the US, for example, 80% of the biogas we generate is flared. But that can be a resource. Now, if we're using the biogas as a feedstock for creating new materials, the opportunities we have is it's cheap and abundant. It's everywhere. It's in landfills. It's in wastewater plants. It's being flared now. It's consistent. That feedstock is remarkably consistent. And we can create a lot of diverse materials from that material. The challenges we have is the microbes are specialized. So it means we need to, it's not just any type of microbe. It has to be methanotrophs. Yes, in a digester, you may have some methanotrophs, but there are some very specific steps we need to take. If it's a refinery, I need to be able to make sure that what happens in this refinery, just like a petroleum refinery, happens in the next refinery and the next one. And then in terms of, so if we look at what's going on here, methanotrophy means you're taking methane and then you're adding oxygen to the methane. That is a recipe for disaster if we don't know what we're doing, right? And then the fundamental challenge we also have is methane is a very low solubility gas. You can only dissolve about 14 milligrams per liter of methane. It's extremely low solubility. Oxygen, on the other hand, is the solubility potential is high. It's about 45 milligrams per liter. So the fundamental challenge we have is how do we take these gases that want to blow up? How do we control how we bring them together? How do we take a low solubility gas and a high solubility gas, combine them, and have a process that makes sense? And by the way, this process generates almost 80% of the heat that you would get from combustion. So how do we control that heat? That is a fundamental engineering problem that process engineers that we need to, in terms of how we address these are issues that we need to bring others into the field to help us figure out. The good news is there are people doing this at a commercial level. So companies like Calista, Mango, and others are doing some excellent things here. Algae, fantastic. We've been, finding ways of extracting the value from algae. About 25 years ago, I was doing a PhD on photo. I was in a chemical engineering department developing optimized photo reactors. 25 years ago, when I was doing those studies, I was using tubular reactors because in chemical engineering, they'd figured out that tubular reactors are the most efficient way if we're trying to use photons, if we're trying to harvest the energy of photons. The challenge we have is light doesn't travel too far in a medium like water that also has solids. So tubular reactor, an annular system where we're able to harvest that light. 25 years ago, those were the things we were doing. It's interesting that it's taken about 20 years after that for us on the wastewater side to start realizing that, if we're trying to extract algae and do it in an optimized way, we might actually have to have tubular reactors. The point I'm making is that it might actually be time for us to take some of the challenges we have and go back beyond the wastewater departments in universities to actually start fundamentally recruiting people on the chemical engineering side, the process engineering side, to help to join us in figuring out what some of these fundamental challenges are. The path to success, I think, it's two major things. Process engineering is critical. If we look at the 6 problems that are highlighted, 4 of them are around taking the processing that we do to a different level. And then the next one is around innovative business models that can allow us to unlock the value, encourage private sector participation, and help us unlock the potential that is in biorefining. Thank you.
Thank you, Malcolm. A passionate speech and some real challenges there about how we consider the products that we can create based on the drivers that we have within our own organisation. So if you don't need a lot of energy because you've got cheap energy, maybe you can do something different with the biogas. So some really good thoughts there. Okay, I shall introduce our next speaker. It's Harald Kleiven from CAMBI.
Okay, good morning, everyone. I've been with CAMBI for 15 years, since we were about 10 people, and helped develop a world market. And currently I'm responsible for developing new markets, Sub-Saharan Africa, Latin America, and India. So we're based in Oslo, Norway. I wanted to just remind ourselves of the goals for 2030. And I will show you some examples. These highlighted goals are some of the goals we cover in some of the plants that are using thermal hydrolysis at its core. And thermal hydrolysis is a pre-treatment system. I'll get back to that. And I hope you will remember after this speech today is that, if you want to do, you can create all these fancy systems for the future, but the big cities of the world right now are about to implement 100-year-old technology. So just to improve that is where we have to start, okay? And I'm all for vacuum toilets and anaerobically digest the wastewater directly and get rid of sludge. But in the meantime, we'll have some sludge and we need to take care of it. The other thing I'm thinking is that if once you put in an infrastructure now, that's going to last for 20, 40 years, make it multi-fuel. So don't make it dependent on sewage sludge, because maybe Frank Rogalla is right. We can make some algae instead, of we can make other material. So co-digestion is very important. I think also that biogas is a core. It's underestimated of its potential to reduce carbon footprint just by avoiding unbridled methane release. We just talked about the permafrost release of methane, but imagine all the landfills in India, how much methane they release. In the 1990s in Norway, they estimated that 7% of the total carbon footprint, the greenhouse gas emissions from Norway was from landfills. And these are good landfills with landfill gas extraction and in a cold climate. So imagine what it is in India. Nobody's measured it. So taking organic waste to reuse it in enclosed systems and use that biogas. And you don't have to make it so complex either. You can use it, you can upgrade the biogas and run buses, and I'll show you. And then you replace diesel, and why isn't that as green as an electric bus when the electricity is produced from coal, So the core to a biorefinery, in our view, is a proper pre-treatment. There are many ways of doing it. We have decided that thermal hydrolysis, not we, but a lot of research have shown that pressure cooking sludge is about 160 to 170 degree for about 20, 30 minutes, and depressurizing it is a very efficient pre-treatment system. That would allow your digester footprint to be minimized. In typical plants, about 1/3 of the digester volume, so you save an enormous amount of land and capex. And then you, at the same time, you increase from a mixed sludge, your biogas production about 20, 30%, plus you increase your dewatability in the final mechanical dewatering. So at the end, you'll produce a low odor, class A, meaning pathogen-free product that is ready to agriculture. But you also reduce the volume. So in case of Tilburg, which we had yesterday, that has for some reasons, they needed to have incineration. They have too much sludge. Maybe the metals are too high. You have reduced the volume. Now, ask yourself, how much does it cost to put 1 ton of sludge to an incinerator or to a dryer? I know the cost we can have, but at least 40, 50 euro. So you reduce your volume. So then you could whatever, but also make it possible to recycle it, because in the end, there was a definition of biorefinery that you gave that actually say we have to reuse the materials. Now, if we are saying that what we produce in our sewer system is so toxic we can't reuse it, then human beings are toxic. What are we doing here, right? Anyway, so I went into some of the advantages that thermal hydrolysis brings, but one is improved quality of product, reduced volume, reduced amount of digester volume. Washington, D.C. reduced their digester volume in the plant digester. Frank was part of the wise men that selected THP for Washington, D.C. They had planned, they used millions of dollars to design a 180,000 cubic meter digester, egg-shaped digester project that in the end became 60,000 or 57,000 cubic meter digesters. The savings was $200 million compared to the original design. Now, special America, very expensive and so on, but that was actually paid by day one. And then you got what I will show you, example of a fantastic product and reduced operating costs by more biogas, and of course adhering to very strict regulation on Class A, which is the 503 regulation, being copycat in a lot of countries around the world. India doesn't have regulation, but Delhi and Mumbai are putting USA EPA 503 regulation in the tenders. The Namami Ganges, who's going to clean 500 million people's wastewater into the Ganges, yesterday was shown a letter where the head director is saying, well, any treatment of sewage sludge needs to have a Class A already. And it's not even a regulation with the CPCB, which is so it's happening. It's just like in America where things are happening in the cities, maybe not on the federal level. So I was just saying that we are part of the nexus of clean air, clean water, sustainable agriculture, and clean water. And This is the example of Washington, D.C. They had 500,000 tons of raw sludge mixed with dewatered sludge mixed with lime. 500,000 US tons is now reduced through anaerobic digestion, and first THP, anaerobic digestion, and dewatering with belt presses, very low energy consumption, to 165,000 tons, so 1/3 almost. And that is now not Class B, it's Class A, so their transport cost is reduced. They can spread it closer. The odor reduction is 70%. They sold last year 40,000 tons as a bloom. They developed their own brand name. They reached out to the community. And we are now in America where court cases happen to come after you if you know, we have odor complaints, whatever, right? So if it could happen in Washington, D.C., I would say it could happen anywhere. So this is a success story where they created this bloom product, and they claim to have sold off the belt press maybe half of that 40,000 tons at $5 or whatever it is. The point is, the haulers, the people who use this for road construction or forestry or agriculture, and even through to stores where they sell them in bags, they start paying for it. They also cure some of the product once it's dewatered properly and it's got the proper texture. You can actually store this kind of stuff and turn it a little bit, and then they have cured this to 60% solids just by curing it. So it's and the operators are very, very proud of what they're doing. Of course, we had DC Water presenting here yesterday, BG George. These are very big systems, so that scares people. So we put in a small one. This is 250,000 PE. It's a CAMBI in a container, basically 40-foot container system that can treat sludge for about 25 dry tons a day. The interesting with this one is that it converted, or maybe was already converted to Bio-P. And when you have Bio-P, you release all the first of all, steam explodes, you release the phosphorus, release everything, and then it's released in the digesters. So you need to capture it. So they have a Struvat recovery system. We've done research with in Norway and Germany, finding the potential to reach the magical 50% recovery of phosphorus in sludge. You have to have some sort of hydrolysis, and thermal hydrolysis, we think, is key to this. And then you have to have a combination of various types of taking out the phosphorus, but this is one example. And this plant also has an anamog system. This is Medina, Ohio. Then these are, if you think of a refinery, wouldn't you think this looked like a refinery? Well, there's the refinery. It's actually doing the refinery work. So what people are talking about, biorefinery, some futuristic thing, no, it's happening. Because these are sludge centers, are sludge recovery centers that produce energy, produce fertilizer, and recover to some degree the nutrients as well. They're already a biorefinery. And the idea with a refinery is, of course, to have lots of pipes and tanks, right? There you go. And so, but what I was saying in the beginning is the key to this is to make a multi-fuel systems. So this is an example that we did for 52 municipalities in Norway, where they actually do sewage sludge, food waste, and fish waste in the same. And there are different zones in the plant, so you can go from a clean zone to a dirty zone and all that, and it requires a sterilization. We think also that to establish a technology base where it's not a fight where is 75 degrees enough to to the bugs to regrow or not, go for 133. That's the sterilization. Well, if you do it, you get all these benefits. Why not make that legislation? That's my challenge to you in the virus times. Kill the bugs. Anyway, and this is an example where we do biogas to liquid biogas at Oslo. So this is food waste, pure food waste plant based on thermal hydrolysis core. We deliver the whole plant in Oslo, and it has source separated food waste from all the households of Oslo, and then it makes a biofertilizer cake, but it also concentrates the liquids through an evaporation system, vacuum evaporator, Evaporation de France, French system. And then they make a liquid fertilizer from the nitrogen. Because they had a zero liquid discharge. It's in the middle of nowhere. It doesn't have a wastewater system next to it. It has a landfill. And these are buses in Oslo run on biogas. But they actually, to get it to Oslo, it makes LNG first, or what do you call it, liquefied biogas. Just to show carbon footprint reduction and other goals for the, so of course we can reduce it. We need the further steps, like you were saying, Frank. It's not enough with 30% and all that, but it does help that United Utilities, and thank you for that, you developed that project on the customer side. They actually put in this system, instead of a new incinerator, tripling almost the throughput of these 8 digesters you see there in the right-hand corner by reducing viscosity by pre-treating the sludge. And then created 10 megawatts electric. They upgrade some of the biogas to run their vehicles, and they separated the whole system for Biosolids into a separate company within United Utilities. And they take less and less to the incinerator because the farmers love the product. And they're very, so the point of this story was that they cut, this was paid for by operating savings, but they also saved 32,000 tons of CO2 per year, measured by United Utilities themselves. 8% of the total emissions of carbon emissions from the biggest utility. Is it the biggest, or is Thames Water? You know, the utility in, you're not with United Utilities anymore. Yeah. So that's an interesting, and the same with, what's interesting is that Beijing decided that we are not wastewater treatment plant, we are resource recovery plant. Everybody's heard of it. PUB is doing the same in Singapore. But is that a biorefinery? Well, that's the discussion we're going to have, you know, but at least it's the step on the way. They want to recycle their resources, and they put in 5 THP plants, treating 6,000 tons of sludge per day. And Bill Barber, your former colleague, estimated that compared to the drying project they had planned, they saved 300,000 tons of CO2 per year. Now, at the current European CO2 price at 20 euro a ton, you can do the math. But he didn't pay for the project. The project was paid by operating savings. So, you know, to do the right thing is also sometimes the most economical. And we just want to mention in this digital world that obviously digitalization is part to our process too. So we offer a system where online measurement of our plants and to do preventive maintenance, to share the knowledge and to optimize the operations of the plants. Thank you.
Thank you, Harald. Fantastic technology. I would say that I put what was the largest on the planet in at Davey, and it was really at a time when circular economy wasn't as used in our language as it is now. But if you think about what it does, in addition to how it ensures that you can utilise your existing asset base. So we didn't have to build huge digesters to treat 3 times the sludge that we put through that facility. So cook your sludge before your tummy eats it is Harald's message. Okay, I shall pass you to our last speaker now. Yeah, there you go. Enjoy your breakfast. Yeah. So our last speaker is Miguel-Sanz.
Thank you, Rick. I think at the last one, after a long time we were waiting just to fulfill the meeting room and the other, but I decided just to change the name, Bio-refineries. Do you have a? So I decided just to change this as the marketing we did in the wastewater treatment plant in our company, just we named Biofactories. In the same way with the desalination in the drinking water was changing the name, not treatment plants, just was really water factories. I think we need to change, not Bio-refineries, because perhaps it's not a very good marketing when we are doing, even when we are doing reuse. It's again. So the circular economy, I think, is better. We say, we decide just to put the name Biofactories, because really it's a factory. We are creating something new, but recycling, recovering, but not using the re in the other. Sorry for the first Frank or yourself when you're using re a lot of time, but the target is the same. It's resource recovery in wastewater treatment plant. So the first idea is just to change the water treatment plant by a factory concept, but with several concepts at the same time. So first, treating all the water arriving to the plant, even from the storm water, when you have a unitary network. The first idea, just in the primary treatment, is the carbon capture, just to recover all the energy you can get from there and all the sludge, all the biosolids. And in the second part of the treatment, in the biological treatment, just to optimize, to minimize the operational cost, reducing the energy, and treating as much as possible, depending what is the target. Because one of the challenges we have in the future in the water, in the wastewater treatment, in the biofactories, is just to treat the micropollutants. We are doing the first in Switzerland, in Lausanne, where it's a challenge, and that's also changing with the way we are taking the sludge, because you are concentrated all these products in the biosolids. So it's something changing, and we could implement some changes in the step. So first idea is just to treat as much as possible, reuse, treat, and the first idea is just to recover the water, to reuse the water, either from the industry, from the cities, aquifer recharge, agriculture, all the multi-purpose. We are doing it in several parts of the world, in California and West Basin, taking the water coming from Los Angeles, from Hyperion plant, and we produce 5 different of waters, independent, adaptive for every customer. And also for agriculture, it's quite similar. We are doing something similar in Perth, in Binjup, also to recharge the aquifer, to have an indirect potable reuse, but also for agriculture. So that's is the first idea. Everyone is thinking in reuse the water, minimizing, optimizing all the resources, all the water resources you have. But the next step is just coming from this last treatment line, but the biosolid treatment line. First is just to try to get all the energy of all the products you have inside. The first idea just to have a pretreatment from the anaerobic digestion, just to produce as much as possible in biogas. The thermal hydrolysis process is one of the best pretreatment, just to increment the methane production, arriving at 60% methane reduction of the volatile material just to become biomethane. But also you have a post-treatment, the HTC, the geothermal carbonization, in order to minimize the biosolid concentration. You can get between 60–70% concentration of dryness in the biosolid, in order to minimize the transport cost, and also all the water is coming from there. You can produce more biogas because they are more concentrated in dissolved organic matter. The other is just, depending what is the treatment, depending if there is micropollutant inside, you can go either to incinerate, because it's the only way when you have a lot of micropollutant into the biosolid. Even if you have the Class A, Harald, you can use in the agriculture because it's full of viruses or things or materials. We are not able just to produce to use in agriculture. Or even with the using incineration, you can recover from the acids some products like phosphorus. And to be used like fertilizer. The next step is, once you optimize the biogas production, is to purify this biogas, even taking the CO2, taking the methane, and use it also in urban services, not only just to introduce into the gas network after purifying and even changing the odor, just to have a better marketing from the product coming from the biosolid, the sludge. You can use it just to produce heat, electricity, but also if you are concentrating or you are even liquefying the gas, using in urban services for short distance. And we have 10 references in France, using in cars, in taxis, in buses of the city, or even you can sell like a liquefied, bio-liquefied natural gas. So it's the other target. We are inside. And finally, even if you are using incineration, you can produce electricity, as we have it, for example, in Bilbao. We have 2 incineration furnaces, and we are producing steam, and with the steam we are producing energy. And you can use the heating. Not in every city you can do it, especially in the northern cities. You could use this heat in the urban services. And the last one, when we are in intensive treatment in the biosolid, you have the opportunity just to first to recover the nitrogen and phosphorus. We have 2 processes: the phosphogreen, just to recover the phosphorus from from the effluent coming from the water treatment, from the sludge treatment, and selling it as fertilizer. We have several references in Scandinavian countries, in Denmark, in Sweden, and Norway, but also using the side-stream anamox. We are doing it as our biofactories in Santiago de Chile or in Orense in Spain. We are reducing the nitrogen they are coming there in order to minimize the energy consumption in the water treatment line. So, but the next step is just to try to recover in this treatment. I think thus we are closing the loop just in the circular economy in the biofactories, reusing the water and reusing everything which is inside, even minerals, nitrogen, phosphorus as fertilizer, and using the biogas as a bioproduct into the city. Thank you.
Thank you, Miguel. Some real examples of how a circular economy is being deployed with what is actually a valuable resource. We don't want to shout that too loudly because people might actually start paying us to, charging us to take it away from them. So, okay, so I think we've got time for a small number of questions. We have gone slightly over time, but we did start a little bit late. So if anyone wants to ask a question, can you say who you are and which company you're from, please, and address the panel.
Andrew Walker from Blue Gold Marketing. I'm wondering about the actual, not only utilization of the good materials and the energy, but what can you do to actually create a market, for example, for some of the good materials which you get out of there? You mentioned grit before, phosphorus, different metals maybe. What can you do to actually get a market to not only get people to pay you to take the wastewater off your hands, but also pay you when you produce things in the factory?
Well, of course, that's a key question because we are just a water utility, and to produce the product and get to the customer, we need the conventional. I think the room is small enough so we can hear each other without mic. But obviously we have to look at the whole value chain and say who are the partners who bring us close to the customer, and that's what we do. We work with Fabyi, we work with plastics transformers to define what their requirements are, what value they currently generate, and how can we integrate into that chain and meet the specs that the downstream value chain expects. But it's a whole new approach for us because today we weren't exposed to these very specific requirements, and all we had to meet was the water regulations, and therefore it's a iterative process to understand the logistics, the cost factors, and the product requirements to get to the market.
Just an appointment, because I think one of the things that's happening in this market is coming from the infrastructure, we are becoming more for services. And one of the main points is just to get where you are customers in this kind of thing. When you are trying to just to recover resources in the other, first, you can do the phosphorus recovery, but you have no customer, no clients just to purchase it. You are wasting your time and your money. So first is just to create the market for everything. So that needs an adaptive solution. Even for water reuse, they need a lot of marketing in the area you are producing. Of course, you need to sacrifice it, you need to subsidize some products in order to create a market. I think is the next 5-10 years work is just to do a lot of marketing and a lot of effort, just selling these services, because finally they are services.
I absolutely agree with that. In the UK, we've set ourselves some very difficult targets in the water industry to be net zero carbon by 2030. And a lot of the water industry in the UK is now asking their suppliers to also be net zero carbon. So the opportunity is there for people to utilise the resources that we can produce from wastewater within the products that they then sell. So I completely agree with Miguel that over the next 5 years particularly, and hopefully quicker than that, people will start to see the value in this and see the opportunity to take something which is a sustainable resource, essentially.
If I could comment on one thing, is what I think is important to have in mind is what Frank was mentioning before. You're competing with a fertilizer factory that has an enormous production in one place and can brand it. And so I think economies of scale will play a role. And the example of DC Water is important because they have 165,000 tons a year of a consistent product, and they use time to develop it, outreach programs, they branded it. And they actually sold 40,000 tons, and it's going up. Their aim this year is 60. And if that happens, there's already a market. And then everybody will say, well, what about what's in it? But their outreach program is including all the protesters. They invite them in, and they do a lot of research. So this requires a lot of resources. So that can only happen on a certain scale. And also, if you don't have enough material to deliver, you can't develop a market. So I'll give you an example. If you have a ton of waste oil, you have to pay 100 euros to get rid of it. If you have 100,000 tons, you can sell it to a refinery, right? So the point is economies of scale.
If I may just very quickly add to that. We're starting to see aggregators. So yes, you might have a single plant that maybe has large capacity, but what about all those small and medium plants for which is going to be uneconomical? So what we're seeing is aggregators. They're not wastewater people, they are marketers. They go to all the different plants, get all the different sludges, so it's one voice, negotiating with retailers, asking them to put products on the shelf. I think we have to continue to encourage more of that, and in markets where we don't yet have that, it might make sense for wastewater associations, not just to be places where we're talking about technology, but where we might actually have wastewater associations partner with a marketing agency that can actually help them collectively market their products.
I think we've probably got time for one more, two max questions. Yes.
Good morning. My name is Jean-Marc Petit, Director of Engineering from Central-San, a water factory in California. Excellent panel, thank you. You touched a little bit in the beginning about PFOS, or PFAS. It's becoming a big issue in the US, I'm sure in Europe too. And so there's already not a full engagement by all the cities to take biosolids and farmers. There's some states right now that are banning actually biosolids. And it's not just concern for agriculture, but it's groundwater infiltration. So I'd like the panel's opinion on that. Thank you.
So throughout my time in the industry, I've been in the industry for 30 years now, there's always been the latest thing that we worry about within biosolids. In the UK, it's 1% of the fertiliser that's applied to agriculture. It's in comparison, it's really small volumes. The organics that we're talking about, these things are in lots of stuff in your day-to-day life. So PFOS is a stain retardant. So you've probably got more in your curtains and your carpet in your house than you've got in biosolids. But a lot of these issues we've seen previously with PCBs and PAHs in biosolids, a lot of this is about source control rather than picking out the biosolids element. The good stuff in biosolids significantly outweighs the bad stuff, and it's about managing that control and the application. You can still take this to agriculture, it just depends on how that then ultimately finds its way into the food chain, into the value chain. So there's a lot of work that's been done in the UK on this over the last 10 years. A lot of chemicals investigation programs, spent huge amounts of money. We're currently sponsoring a PhD looking at the mechanisms of how it actually manifests itself throughout the environment and where it ultimately ends up after application. So there's lots of, we can have a conversation after, but there's lots of work being done in the UK on this. Yeah.
Just a quick, my thinking is that, yes, some places you have to put an incinerator because that's what you have or whatever, but once you have an, if India and all these projects that or countries that I'm responsible, what are we advising them to do? Now the cost of incineration and drying is very high, so advanced, and it's a linear. Once you have that in, where is the incentive for the politicians to clean up that tannery with chrome 8 emitting into the sewer? None, because you have an incinerator at the end. So if you want a circular economy, you have to make sure you put something in that incentivizes the whole system. So, for example, DC Water has an EQ standard, which is very low on metals, and they're going to go after anyone emitting bad stuff into the sewer. Now you have to also ask you in the end then, is what we eat, the pills, whatever, is that toxic enough, what human beings, should it be taken out of the equation of circularity? That's another question. But I don't think so. I think the USA EPA approach with risk versus risk approach is shown that the risk is very low if you control the source, as you're saying. And in the end, we don't want these PAH, these toxic into our system anyway, right? So create a system that incentivizes to get rid of the pollutants going in the first place.
Just only one small comment due to the PFAS, because in USA it's an issue, but in Europe it's involved in the same all micropollutants, and all these kind of things is under study, there's under revision. This is one treatment in the water treatment line, but there is a consequence in the sludge treatment. So it's, but it's one of the materials. Otherwise, you can see to the film this week. So just look in some film coming from DuPont, because PFAS, part of the scene is producing from Teflon. Teflon is a DuPont product. So we are in the screens this kind of matter.
It's going to keep coming up, and it's actually, as you said, preventing the adoption of biosolids. So whether it's real or not, we have to solve that problem. And I think bacterial methods would be part of the solution. The reality is the microbes that treat it are not in a digester, right? That is where we concentrate. So part of that solution set will have to be rethinking what we're doing in digesters, and perhaps intentionally putting in microbes that are there not because they help digestion, but because they help PFOS reduction. So those are some of the things that we're starting to look at from a research perspective.
Okay. One more question. Can we squeeze one more question out, or do you think? I think we're probably going to well over our time. I'm being given the signal to stop. Okay, so fine.
I think everybody should have one more beer.
So can we just thank the speakers again? Appreciate that.